velocity. The purpose of this lab was to identify the differences between the predicted and observed motion of an object with constant velocity. In this lab, I used tracker and code to make graphs about the position, time, and velocity. I added calculations using the momentum principle when applying Newton's second law and other physics principles, such as net force being zero when there's constant velocity, and the formula that expected constant velocity be the overall displacement divided by change in time. The results of this lab showed that the predicted motion of an object at a constant velocity was a straight line, and the observed motion had some more fluctuations in it. The differences between the lines graph was not great and shows that the object was moving at constant velocity. The main physics principles I used in this lab are the momentum principle, where I know that net force is equal to the change in momentum or change in time. And I also know that momentum is mass times velocity, so I can conclude that if velocity is constant, net force is due to Newton's second law. If force is constant, I can use the equation below related to kinematics. I can also apply the velocity and position update formula since I know the force is constant. The full kinematics equation can be derived from these two equations. Since this lab focused on constant velocity, I'm able to assume that the net force is zero because the velocity does not change and the object is not accelerating. I also know that the gravitational force acting on the object will cancel out with the normal force, assuring that the force on the object is zero. This also leads to conclude that net force is constant. The force equation below, F equals mass acceleration, helps us see that when acceleration is zero, so is force. I can also use the simple equation below to solve for velocity, since I know velocity, when constant, is displacement divided by time. All of these equations and rules help us to understand the motion of the object in this lab and make accurate calculations. I also assume with these calculations that there is no air resistance or friction since it is negligible in this lab. The system in this lab is the moving marker, and the surroundings are everything else video, such as the table and anything near the mark. The initial conditions for the lab are that the marker starts at its constant velocity, 0.208 meters per second in the x direction, and its position starts at the origin, the zero vector. In the experiment, I rolled a marker on a flat surface and captured its motion in a video that I analyzed in Tracker. This allowed me to find the exact positions the marker was at certain times relative to the starting position of the marker, the set origin. The experiment with the data obtained from the tracker, I was able to calculate the velocity of the marker using the equation below. By dividing the total change position by the total change in time, I found that the constant velocity of the marker should be 0.208 meters per second. That is why I used this value as the initial velocity value in my code. The time and position data came from the very last data point tracker, so I could account for the overall change in time and position. First, in the code, I changed the net force vector line 56 to 0, because of the constant velocity. Next, I had to update the marker's velocity and position using, you guessed it, the velocity and position update formulas as seen in lines 60 and 62. The marker's velocity is equal to the original velocity, 0.208 meters per second, plus the net force divided by mass and multiplied by time. The net force is zero and mass cancels out, so I left the vector unchanged since velocity does not change. The position, however, does change and is equal to the initial position, 0, plus the change in time times the average velocity, which is just whatever the current timestamp is, times 0.208 meters per second to the constant velocity. Those calculations in code output a model that predicted the marker's motion in the graphs and a visual. Here's the model that I made of predicted versus observed position. These lines are very similar, which shows us that they're constant velocity. The data from the predicted model red and the observed data blue are very similar, but are not exactly the same. Predicted data points make a straight line showing that the predicted velocity is constant. The observed data shows some fluctuation, but it's almost a straight line. This is because the model uses the kinematics equations to calculate the velocity of the ball according to the momentum principle and Newton's second law that assume perfect conditions in the surroundings. This is not quite the case in the real world, where friction and air resistance exist and have an effect. This is a possible source for error. Human error could have also caused these differences since I had to click for the position of the marker for each data point, and I tried to be exact but could not be every time. This is probably one of the main reasons for the differences between the lines in the graph. In conclusion, the lines are very similar because the marker is moving at practically constant velocity. Now, if you flipped the x-axis, so x positive was now negative, not much would change in terms of results. The magnitude of the velocity would not change because the marker has the same motion, just in the opposite direction. The x part of the velocity would become negative since it is moving left away from the origin, but the conclusions would stay the same. Is it possible for you to see how many forces are being added together to give net zero force in the case? This is something you can assume if you know all of the forces. I know that the marker starts in motion and the gravitational force and normal force cancel out since it is on a flat surface, but we did not account for friction, air resistance, and the push that occurred before time equals 0. So you can see that there's two forces, normal and gravitational, that cancel out to give us zero net force in my calculations.